Howdy. I hope you stay well. It's been almost 3 weeks since we moved everything to online. I appreciate your patience and participation. Uh, I'm still learning this and that things for online lecture. Please bear with me. Today is reading day, so no class, but we fell behind a little bit. I just wanted to provide this video to cover page 5, 6, and 7 of our note. So we will start the real discussion on eigenvalues and eigenvectors on Monday. I just wanted to finish our discussion for Gauss-Jordan elimination, page 5, 6, and 7. All right. I'm sharing this note. I hope you can clearly see this note. All right, so quick review. So in this chapter, we want to discuss system of linear differential equations. Every system of every system of first order differential equations can be expressed as matrix equation. So we want to understand the matrix, especially in terms of eigenvalue and eigenvector. Then we will use some theory to solve the system. So to find eigenvalue, we need to know how to calculate determinant of the matrix. To find eigenvector, we need to solve system of linear equations. Now that we will be working with 3x3 matrix, we discussed how to find determinant of 3x3 matrix. Actually, you can use any row, any column to calculate the determinant. And to find the eigenvalue, we need to solve system of linear equation for 3 unknowns. So we will use Gauss-Jordan elimination. As I said, this is nothing new. We know how to solve system of linear equations. The thing is, now that we will work with 3 unknowns, we need to make our writing simple and short. So Gauss-Jordan elimination is all about writing our calculation in a short and clear way. That's it. So one way is to use matrix expression. It's matrix multiplication, for example, and then you can eliminate this redundant x and y in this right column. And so eventually, we can use augmented matrix. So we suppress x and y, we take only numbers. So reading this system, we have this matrix 2, 3, 1, 1 for the left-hand side and 1 and 3. You put vertical bar to separate 2 sides. Then we have augmented matrix. Then you apply the same operation as you solve system of equation as usual. The same idea it's nothing new. So eventually, what we want to have is identity matrix 1, 0, 0, 1. So we apply operations to have 1, 0, 0, 1. Once we have identity matrix, we are ready to write down the solution like this. So one more example. In example 4, we have matrix 1, 2, 2, 1. And we apply some operation to have 1, 0, 0, 1. Once you have this identity matrix, we can write down the solution right away. So having 1 on the diagonal is very helpful. Once you have 1 on the diagonal, you can use this easiest number to do whatever you want. So having 1 is always useful and helpful, and eventually you want to have identity matrix. Actually, our result will not be always identity, actually almost identity. So chances are you will get matrix like this, 1, 0, 0, 0, 1, 0, 0, 0, 0, or 0, 1, 0, 0, 0, 1, 0, 0, 0. So look at the bottom rows. Those bottom rows have only 0 entry. Those rows are called the 0 rows. Okay, so now that our discussion is all about writing our calculation in a short and simple way, let's use notation. So elementary row operations, so we can apply 3 operations. Here is notation. So multiply a row by a non-zero number. So the notation is constant or scalar C times Ri. Again, R sub I is ith row. So in the previous example, we had 0, -3 with -6 in the bottom row. And then we multiply -1/3 to the second row to have 0, 1, 2. So this is always possible. So whenever you want, you can multiply a row by a non-zero constant. The notation is C times Ri. You can, of course, interchange 2 rows. The notation is I sub R, I, and J. So this is to exchange ith row and jth row. So this is exchange Ri and Rj. And then you can add, number 3 is actually very useful. You can take any multiple of a 1 row, add this to any other row. So notation is C times Ri, you add this to jth row, and then you can, well, depending on your textbook or web resources, they use this notation, but I prefer even more information. So I prefer this notation. So you want to indicate this, where this operation has effect. So this has effect on jth row. So you are replacing jth row with this operation, C times Ri plus Rj. So let's use those 3 notations for those 3 operations. Okay, example 5. So you can start with taking augmented matrix 1, -2, 2, -4, 1, 0, 0. One interesting thing is we have only zeros in this column. Good. Well, eventually you want to have identity matrix. Well, it's obvious to have identity matrix. So you want to eventually have 1, 0, 0, 1. But once you kill this number 2, so you need 0 in this position, right? And to kill this 2, what you can do is to take -2 copy of first row, add this to second row. This has effect in second row. Good. That means first row, sorry, the first row is not correct. First row will remain. Now that this operation has effect only in the second row, the first row will remain like this. So 2 minus 2 is 0, -4 plus 4 is 0, 0. That's it. So somehow our bottom row is 0 row. Everything is 0. Good. You think any further operation? Do you see anything else to do? No more operation. So we stop there. So let me write here. So no more operation. And actually we are done. And then we interpret this by using x and y. So, oops, let me use Blick. So you put x and y back into this system. So you interpret. So once you are done, or if you see no more operation, you interpret your result by putting x and y back, and then you take multiplication. First row, 1 and negative 2 with xy is x minus 2y equals 0. Look at this second row. Second row says 0x plus 0y is 0. Probably says 0 equals 0. I agree. It's completely true, but it doesn't say anything. 0 equals 0 is true, but we don't need such a thing. So let's focus on this equation, x equals 2y. So that means x equals 2y. Good. How do we understand this solution? Well, geometrically, you can plot this equation because the slope is a half, so it is a straight line. So let me draw the graph. Y equals half of x. That's it. And it turns out that geometrically the solution, all points on the line, x equals 2y or y equals half x. So basically we have infinitely many solutions. Every point or all points on the line will give you a solution. You may think it's a silly case. Yes, it's a silly case. Actually, look at this system, x minus 2y equals 0 to x minus 4y equals 0. Two equations are identical. Two equations are equivalent. So that's why if you take intersection of two lines, we have the line itself. The solution is all points of the line. So the point I want to make is that now that we have infinite solution, we need to know how to express such a thing. Again, we are not going to list or write the points one by one because we will die before we finish. And we want to know how to express such a thing. That's the point. Actually, we will use this way of representing infinite set of solution when we study eigenvector. So this is quite important. That's why I'm putting this example. So the idea is to represent this infinite set of solution. We use parameter. Conventionally, people use letter T. Letter T for, it's up to you. We have two letters, x and y. I mean, two variables, x and y, but traditionally, people use parameter for later or second variable. Okay, so look at this x equals 2y. X equals 2y, that is our result from our calculation. What you want to do, you express x and y as column matrix like this. Well, x equals 2y, so x equals 2y. You may think it's silly. Y is y. It's silly. But the point is, you express everything in terms of y. So express everything in y. That's what you want to do. In this column, you express your column matrix in y. Now you replace y by t. So if you replace y by t, we have 2t and t. in the column. So we have this column matrix. So far we have x and y, 2t and t, with the parameter t. Once you factor everything by t, we have t times some certain vector 2, 1. Here, 2, 1 is not a random vector. Actually, this is 2, 1. 2, 1 is actually direction vector of the line. Here is 2, here is 1. Now you see, t times 2, 1 is one good way to express entire points on the line. One thing to add is you declare your t can be any real number. So this notation is any. The set of all, let me rewrite this. This notation, fancy capital R, is the set of all real numbers. The set of all real numbers. So by putting this condition, t can be any real number, you are declaring that the solution x and y can be any multiple of the vector 2, 1. So that's exactly what we want. All the points on the line can be expressed as any multiple of the vector 2, 1. So this is how to express infinite set of solution. Well, I think you discussed this way of representing in Math 151, especially when you studied parametric equation. This is one way to express infinite set of solution or infinite set of vectors. So let us use parameter, especially when we work with infinite set of solution. Good. Here is a very crucial remark. So when we study eigenvalue, eigenvector, we will use this remark. So this remark is about dichotomy between two matrices. In example 4, our matrix was 1 to 2, 1. 1, 2, 2, 1. Determinant of this is what? 1 minus 4 or negative 3. The point is this is non-zero. Actually, there is a beautiful theory saying that whenever the matrix is non-zero, the solution is always unique. Actually, we got 1 point on the plane for the solution. However, in the previous example, the determinant is, where was the matrix? 1, negative 2, 2, negative 4. I mean, the previous example, 1, negative 2 to negative 4. The determinant is negative 4 plus 4, 0. So there is quite clear dichotomy, some clear difference between matrices with zero determinant and non-zero determinant. Whenever your matrix is zero determinant, the corresponding system of linear equation will give you always infinite solution on the plane, or on the space. So, so far, I think you got familiar with system of linear equations with unique solution or non-zero determinant. From now, we will be working with matrices with zero determinant, which means we will be working with infinite solution. Okay. Example 6. So just one more quick example. So look at this example. Even before solving this example, you can tell whether the solution is infinite or not. I'm giving you some time so that you can guess or you can determine whether it has infinite set or unique solution. You simply look at determinant 4, -2 to -1. Determinant is -4 plus 4, which is 0. That means this system involving this matrix has infinite solution. Yes, actually, if you use augmented matrix for -2 to -1 with 0, 0, well, you will see, I'm skipping the details, but you will see it will be reduced by 1, -1/2, 0, 0. Let me emphasize this, as we have 0 row again. 0 row is a good sign of infinite set of solution, and we want to express this infinite set. So to express the infinite set, we need to use parameter. So first, we interpret this result 1 -half 0, 0, where the xy is 0, 0. So first row with xy is x minus half of y equals 0. That's it. The second row will not give you anything new. 0 equals 0 is always true, but it doesn't give you anything. So look at this. X minus half y is 0. That is our infinite solution. So you want to express this infinite solution using the parameter. So what you can do is to express x and y in terms of y. If you solve this for x, our x is just half of y. Good. Y is y. This is silly, but what you want to do is to have column matrix with each entry in y. Now you introduce parameter t to replace your y. So half of t and then t. This is what we have. Once you factor, what's left is some vector, half and 1. So that means, well, once you allow t to be any real number, this solution is any multiple of the vector 1/2, 1. So 1/2, 1. The vector looks like this with the slope 2. It's not clear. Let me rewrite this. So vector is, I don't like this 5. Yep. So we have a vector. So you're taking any multiple of this. This is good enough. The reason I picked this example is that if you want, you can take different vector. Now that you are taking any multiple of this vector, you can take double of this vector. Let me use different color. Let me use green. What if you use double of this vector with coordinate 1, 2? Now that you are taking any multiple, the same set, 2 and 1. This is always possible. So when you work with infinite set, you can take any multiple. So let me write this here. One can take any multiple. So the second one looks better in the sense that 2, 1 are whole numbers. So instead of using fractions, you can use whole numbers. by taking multiple of your vector. So in case you have some fractions like 1/2, 1/3, 2/5, whatever, you can take any scalar multiple of the vector. Then you will get a little bit better expression. I'm running out of time. Okay, probably the last item. So we apply those operations to turn augmented matrix into something. So I want to make things clear so that what our goal is, and when you see, we stop. So this is about our goal or when to stop. So how do you know when we are done? So those 4 conditions will give you the criterion. Those 4 conditions will give you the answer. So we want to apply Gauss-Jordan elimination to turn augmented matrix into something nice, satisfying those 4 conditions. So let me write the terminology. Reduced, so people call this reduced row echelon form. Well, echelon looks like this. That's why we call this row echelon form in the result. But anyway, in short, this is called RREF. So RREF. So first condition is first non-zero entry in each row. Each non-zero row must be 1, bloody 1. Do I have an example? Probably not. Okay, so in each non-zero row must be, in each non-zero row, the first non-zero entry must be 1. And number 2 is quite long. In consecutive non-zero rows, upper one, lower one, there should be some rule. First entry 1, this bloody 1, in the lower row must be to the right of the bloody 1 in the above row. So let me pick some example. Say you have matrix like this. Suppose you have 2 consecutive rows. This is what I meant. The 1 in the lower row must be to the right of the 1 in upper row. So those ones are not random ones. Those ones are first ones in each row. So this is okay. What if you have ones like this? Say you have 1 here and then 1 here. Look at this. This one at the lower row shows up to the left of this one. In that case, you simply exchange. You can apply exchanging 2 rows. Then you will get the first case. Apply interchanging 2 rows. This is what I meant in condition number 2. Condition number 3 is clear. 0 rows must be at the bottom of the matrix. And number 4 is also very important. A column. This is not row. Let me emphasize this. In each column, if you have bloody 1, in each column, if you have bloody 1, this bloody 1 in number 1, everything else in the column must be 0. Has 0 everywhere. So let me finish this just by putting some example. One example, which is RREF, is identity. One's on the diagonal, 0 everywhere else. Number one, you can check all four conditions. Number one, the first non-zero entry is 1. Yes, in each row, the first non-zero entry is 1. It's not like 2, 3, negative 1. In each row, the first non-zero entry is 1. That's good. Number 2, whenever you pick 2 consecutive rows, the 1 in the lower row is to the right of the 1 in the higher row. That's what I meant. Number 3, 0 row not at the bottom of the matrix. Well, it has no 0 row, so number 3 is satisfied by the same reason. Number 4, a column containing bloody 1 has 0 everywhere else. Let me emphasize this. Look at, for example, column 2. You have 1 here, this bloody 1, and then 0 everywhere else in this column. So in that sense, this is RREF. So identity matrix is clearly RREF, reduced row echelon form. So once you get this identity, you're done. Unfortunately, our result will not be identity. Our result is rather something like almost identity. So for example, I'm going to put 3 more matrices like this. Let me use the middle one. So for example, our result will be something like this. Do you think it's RREF? What do you think? Does it satisfy all 4 conditions? Yes, it's RREF. Condition number 1, in each row, first non-zero entry is 1. The bottom row is just a 0 row. And in each column, once you have bloody 1, everything else is 0. This is RREF. What if you have matrix like this, 0, 1, 0, 1, 0, 0, 0, 0, 0. This is not RREF. Because number 2, this bloody 1 in row 2 shows up to the left of this bloody 1 in row 1. In that case, you apply exchanging 2 rows or row 1, row 2. So you exchange 2 rows, row 1, row 2. Then you will get this RREF. One more. What if you have this matrix, 1 there? Do you see why this is not RREF? Can you tell me? Look at this 1. This one is not the first one, right? We have first ones, the bloody 1, in row 1, row 2. Those are bloody ones, the first non-zero entries, which are 1s. But this one in blue bubble is just a generic number. It happened to be 1, but it's just a number. Look at this number 4. Every column containing the bloody 1 has 0 everywhere else. This is not RREF because condition number 4 is not satisfied. So you want to kill this, right? How do you kill this? You apply some operation. Can you tell me the operation? So you can apply multiple, taking multiple of second row, and then add this to first row. This has effect in first row. Then you will get this RREF. Yes. Well, sorry, this is, well, I meant to have it about half an hour, but it's a little bit more than half an hour. Okay, now that we are fell behind, let me make some change. Homework 8 will be due not next Wednesday, but next Friday. So I don't think we will cover all the examples by next Monday. So let me use red one to write this somewhere here. Yeah. Homework 8 is by next Friday, April 17th, Friday. I'll send out email to make this clear. So homework 8 is not by next Wednesday, but by Friday. So hopefully we will cover all the examples next Monday, and then Wednesday, then you will be fully ready for this homework. All right, we will continue. Have a great weekend. Thank you very much.